Why?
Because phase is the smaller axis, frequency is the longer axis.
And what happens in rectangular field of view?
When you change a rectangle, a square to a rectangle, you just need to change the phase of it. You cannot change the frequency.
You're almost there. You're so close.
When you shrink a field of view,
Yeah.
shrink.
Whenever you go from a square field of view to a rectangular field of view, the phase direction is the one that shrinks, right? That's what she was saying. She was really saying that. But to be a little bit more clear, we have a 20 by 20. Let's say it's a sagittal spine. Which direction is our frequency direction?
It's head to toe.
S to I, which makes our phase direction
Anterior, posterior.
A to P. Okay? So we take that 20 by 20 field of view, and now we're making it rectangular. So our phase direction is going to go from 20 to 10. Depending on how you set your rectangular up, if you do it 50%, it's going to go from 20 to 10. If you only do it 75%, you see what I mean? Your numbers are going to change. But it always shrinks in the phase direction. So why is that important to know? Why is that important to know? Generally, mostly all the time, the long axis of the image is the frequency direction, correct? And the short axis is the phase. Have any one of you in here witnessed or participated in swapping phase and frequency?
Yes.
You have. Tell us about
So,
it.
Phase wrap.
so it was a
Phase wrap.
Phase wrap is one thing. What's another thing?
Is that when you want to change the direction?
Okay. I'm gonna help you.
Okay.
Motion is typically seen in the phase direction. Okay? So let's say we have a sagittal lumbar spine. What's our phase direction?
It's anterior, posterior.
Anterior to posterior. Patient's a big, deep belly breather. Belly's located right there, right? Right where we're trying to scan. So if the patient is taking in big, deep breaths, I'm going to get motion in the phase direction, which would be A to P, which would be what? Right through the spine, right through the cord. If I swap my phase and frequency, and I make my phase direction now inferior to superior, and my frequency direction anterior to posterior, when that belly breather is breathing, where's that motion going to go? Oh, away from the cord. It's going to stay out here, but it's going to travel this way.
Isn't that why we have a sat band in the first place?
It's not the only reason. We use sat bands to saturate out flow, more for arterial flow. Thank you. Okay. The breathing, if you got one of those big belly breathers, you're not going to get rid of it. So if I swapped my phase and frequency, and I set up rectangular field of view, what's now going to happen?
Can't you get wrapped?
So the phase,
They cut off your anatomy.
Why?
Because
It's going to shrink in the phase. It always shrinks in the phase direction. So if you swap your phase and frequency and now your phase direction is S to I, okay, and you decide I'm going to cut my time down, so I'm going to use a rectangular field of view, now it's going to cut your field of view this way instead of front to back. Make sense? So that's why you always have to be careful and be cognizant of where your frequency direction is and where your phase direction is. Does that make sense? I'm not confusing. Good?
I've never seen it before, so I mean, you know, usually we don't swap.
Right, okay, so this, I guarantee you that some of their protocols, it's swapped. This is you guys' opportunity, now that you're learning this stuff, to watch for it more. Before, you're worried about, oh, I gotta cover the anatomy, I've gotta worry, I've gotta make sure that my slices are where they're supposed to be. Okay, now we had a toe in the water last semester, now we're submerging a foot, right here, just 1 foot. We got a foot in the water, okay? So start noticing these things. Look on the machine on where the parameters are and start recognizing, where the phase matrix is, the frequency matrix. On the GE, you'll see it'll say, I don't know if they're all set up the same. Now that I'm thinking about it, I think the 450W, whoever's in Jupiter and is on the Y4, the screen is definitely different, but typically on my GE scanner, I have my TE, my TR, my flip angle, my bandwidth, all in a row. Then I move over, the next column is slice thickness, slice spacing, okay? Then over to the right more, I have my frequency matrix, my phase matrix, my number of necks, okay? And then I have my, whether it's phase or frequency, whichever direction it is, okay? Underneath or over to the right of that. So just start focusing in on where the parameters are and just take note of them, mental notes, looking at them and seeing, try to pick up where your phase direction, your phase and frequency direction is on your scanner.
In Siemens, is the first row on the left,
Okay?
phase direction.
So try to catch these things, and once you see it, then think about, okay, what plane am I scanning in? Okay? And however it's set, let's say, you're doing a sagittal, and it says your phase is A to P, or your frequency is S to I. And then say, okay, yeah, that's how it normally is. If it's set up the opposite way, then A, you're not using rectangular field of view, right? That your phase and frequency has been swapped. Okay, just try to, notice where your matrix is and all these different parameters that we're starting to employ. I know we've seen this before. This just basically shows how the signal, you have a higher signal with your coarse matrix at 128 by 128, the pixels are bigger, right? Now let's go to 128 by 256. Look how it dropped our signal 50%, but we have more pixels, they're smaller. What's happening? What's starting to happen here? Less signal, what else? We're increasing our spatial resolution. Now let's come over here. Let's go to 256 by 256 matrix. Here our signal has gone to 0.35, but our spatial resolution has gone way up. Okay? Because we have more pixels in the same amount of area. Again, uneven matrix, 256 by 128. The larger number, or the first number, is always the frequency encoding. The smaller number is always the phase encoding direction. This yields the rectangular pixels when you use the square field of view. So 256 by 128 is an uneven matrix or rectangular field of view. So the larger number is the frequency direction. The smaller number is the phase direction. Why? Because it always shrinks in the phase direction. Okay? First number is always frequency direction. The second number is always phase. So you're not gonna do a 128 by 256. Why?
You don't change the frequency.
Because that makes your frequency direct, I mean, it's not gonna happen. You're never gonna see the first number or the frequency encoding direction in the matrix smaller than the phase. Rectangular field of view, just went over that, using rectangular field of view it will cut down your scan time. However, the field of view is always decreased in the phase direction. This allows for a decrease in the number of phase encoding steps, which will reduce the overall scan time of your sequence. So again, if you're looking to cut some time and you have a 256, I'm just throwing numbers out there, guys, 256 by 256 matrix, your first number is frequency, your second number is phase. You can drop your phase encoding down to 224. It will increase signal, decrease time. Okay? When you use that rectangular field of view, it automatically does that to you, to your image. Okay? It's going to shrink in the phase, always shrinks in the phase direction. Okay, questions about matrix, field of view, NSA, slice thickness, rectangular field of view. Everybody good? Yes? Good? Okay. All right, let's go to pulse sequences and review. Okay, so types of pulse sequences that we do. We've talked about spin echo and gradient echo. Spin echo being 90-degree excitation pulse followed by a 180 rephasing pulse. Gradient echo, variable flip angle on our excitation, right? To flip. Right, and then a gradient of opposite polarity used to rephase. So now we're going to look at a few different types of pulse sequences. We're going to look at inversion recovery, which Jamarly was talking about earlier. We have stirs and flares. We're going to talk about gradient echo a little bit further than just T1 and T2. We're going to talk about coherent, incoherent. And then we have ultra-fast techniques. Echoplanar. SSFSE means single shot fast spin echo. How many of you guys, I mean, I know all of you guys, diffusion. When do we run a diffusion? Brain for strokes, right? What does that sound like? Loud.
Yes.
It's like bitty, 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 right? What is it doing when it goes bitty, bitty, bitty?
Great.
If you're watching your screen, do you see an image pop up each time you have bitty, bitty? No? Not always? You sure? Does part of it come up? Some of it. That is, a diffusion is an ultra-fast sequence and it's a single shot. Okay? Watch that a little bit more carefully. Listen to the noise. You guys are going to get to the point where you can close your eyes and just by the sound know what type of pulse sequence is running. You will. You'll get there. Okay? So let's talk your conventional spin echo. 90 excitation pulse followed by the 180 rephasing pulse. One line of K space gets filled per TR, also referred to as just spin echo or SE. If you ever see that, just SE, just like we've seen FSE. SE is spin echo. Bessie is fast spin echo. So if you look at a diagram, there's your 90-degree excitation pulse. What happens during the application of the 90-degree excitation pulse?
Yeah, and then you put it in the horizon.
Yeah, but what else happens? What gets turned on during the application of the 90-degree? Slice select gradient gets turned on, remember? Remember that from last year? All right, it's the same. So if you're looking at a diagram of a pulse sequence, did we do one last semester? I think we did just spin echo and gradient echo, right?
Yeah.
Okay, so here we go. 90-degree excitation pulse, slice select gradient gets turned on. 90-degree gets turned off, what happens next?
Phase.
The phase encoding gradient gets turned on. Phase encoding gradient gets turned off before the application, right? Of the 180-degree rate phasing pulse, which is right here on your diagram. And then when that gets turned off, you listen for the echo and the frequency encoding gradient gets turned on. So if you ever see a diagram that looks like this, a 90, 180, and then it says repeat over here, and you see slice select, phase encoding, and then frequency encoding, this is a spin echo. Okay? So again, here's your timing, your RF, 90-degree, your slice select gradient, then your phase encoding gradient, then your 180 rephasing, and then your frequency encoding gradient. There's your echo, there's your signal. Okay, we're good with diagram for spin echo?
So we could use both. When
What's
they're
that?
testing us, they could use either or diagram for just title.
Yeah, you can see it look like this, or you can see the actual peak. Okay, but if you see a small one, and you see, this GS stands for your slice select gradient. GP is your phase encoding gradient. GF, frequency encoding gradient, and this is your signal. So if you see a diagram that has, this is your RF, that's your excitation. You see your slice select on, and you see that off. See, this is off here. And your phase encoding's on. Then your 180, and then your frequency encoding. That is a spin echo diagram. 90, 180. And then here it's starting to go all over again. Okay, make sense? In conventional spin echo, how is our weighting done? We have T1, we have proton density, we have T2. We already know short TR, short TE for T1, long TR, short TE for proton density, and then long TR, long TE for a T2 weighted. This is in spin echo. This C stands for conventional, which means it's not a fast spin echo, it's just a 90, 180, 90, 180, okay? What are the advantages? You get good image quality. It's pretty versatile. You can use it in any body part, okay? And you get a true T2 weighting. Does anybody know why you get a true T2 weighting?
It was the 180 phase.
What happens in a fast spin echo? Multiple 180s. So you get a 90 and you get multiple 180s. In a fast spin echo, your TE is not a true TE. What does that mean? If I select, let's say we're doing a fast spin echo T2, if I select 85 as my TE in a conventional spin echo, every time the excitation pulse comes on, it's a 90 degree, okay? Every time the 180, it's a 180, one time, 90, 180, 90, 180. my TR, and my TE. My TR will always remain the same, but in a fast spin echo, every time you increase those, the 180s, it takes an average of the TE. So instead of me setting an 85 TE and I get an 85 TE every single time, it kind of varies each time. It's going to stay in the T2 range, but it could be anywhere from 75 to 85. Okay, so let's say we have 10, an echo train length of 10. What does that mean? 10 180s, right? Each time that 180 hits, that TE may not get all the way up to 85. So in the 10 180s, let's say I hit 85 twice, but I also hit 75, 78, 82. It's going to take all of those TEs that hit each 180 and it's going to average them together. So my TE now becomes what's called an effective TE. An average gets taken of all 10 of those TEs that were performed each 180. Okay, so if you look at your screen or your image, you'll see it'll say effective EFTE. It's not a true TE. You may set 85, but your effective TE may come out to 81. When you do a conventional spin echo, you get 190, 180. So you get the same TR, well, you're going to get the same TR also in a fast spin echo, but your TE is the exact that you set it on a conventional spin echo, because it's only done one time. Does that make sense? So that's where you get true T2 weighting from, because your TE is exactly what you set it. As long as you set it within T2 parameters, okay? So you have to set it a high TE. Does everybody understand that? Make sense? Okay. Disadvantage, they're longer. Why are they longer? You always do the 180 after the 90, but remember, why is it called fast spin echo? You're using multiple 180s, but it also cuts your time down. Okay, but it also makes your TE an effective TE instead of a true TE. Okay? Fast spin echo begins with a 90 excitation pulse followed by multiple 180s. Each echo has its own phase encoding slope, right? Multiple lines of K space are filled during each TR also. So it's also referred to, I know in Philips, it's turbo spin. What is it on Siemens? It's turbo spin, okay. So for Siemens and Philips, it's called turbo spin. In GE, it's called fast spin echo, okay? So each echo has its own phase encoding slope, so multiple lines of K space gets filled during each TR, makes it a lot quicker. Your timing diagram. This is all you really need to see. There's your 90, 180, 180. This means your echo train length is what? 2. So if you see another one over here, 3. Then you see a small, that's beginning the next, okay? So 90, 180, 180, depending on whatever this one is. If it's a smaller one, it would be 90. This, if it starts out as 2, will stay 2.
So if you change the parameter of your echo train,
Correct. That changes the number of 180s that are performed.
so if you increase it, it increases your time?
No, it decreases your time. That's why it's called a fast spin echo, because You have multiple echoes there, and you have multiple lines of K-space that get filled. Okay? When is an image complete? When all the lines of K-space are filled. So if you're filling multiple lines of K-space, it's going to be faster. But again, remember that TE factor in there, okay? It becomes an effective TE, so it's not really, as they call it, true T2.
So you really wouldn't want to mess with that if you're doing a T2.
No. Put it this way, what is TE control? T2. So if you're doing, this might get a little confusing, if you're doing a fast spin echo T1, you want to keep your echo train length short because you don't want your TE to be wandering because TE controls T2. So you want to make sure that you have diminished T2, obviously in a T1 weighted pull sequence. So typically, the numbers for your echo train length on a T2 are longer. All right, let's look at it this way. T1, short TR, short TE, right? Proton density, long TR, short TE. T2, long TR, long TE. Fast spin echo, T1, still short TR, short TE, a short echo train length. Proton density, short TE, long TR, medium or middle echo train length. T2 weighted, long TR, long TE, longer echo train length. Okay, so let's put numbers to it. T1 weighted, short TR, short TE, short echo train length. Me, personally, I don't go above 4. I'll use 2, 3, or 4. I typically don't make the echo train length greater than 4 on a T1 weighted image, T1 weighted contrast, trying to get T1 weighted contrast, because the TE. Remember, on a fast spin echo, it's not a true TE, it's an effective TE, so an average gets taken. So let's say I chose 25 for my TE. I'm not going to get 25 each time. The longer I do that echo train length out, the greater chance that I have that my TE is going to go off. But either way, it could go longer. What happens if I have a longer TE? Now, I'm not going to get T2 because my TR is still down, but right. I'm hurting my T1 weight. Okay? So when I want on a fast spin echo, short TR, a short TE, and a short echo train length. If I want a proton density, I'm going to use a short TE, a long TR, and a medium echo train length. I use anywhere between 7 and 10. Because remember, that TE is so important. So on a T1, if I go above 4, now I'm starting to get bigger ranges or more ranges of TEs. I can start diminishing my T1, so I want to keep that short. Proton density. I want to keep it medium because proton density is in the middle of T1 and T2, right? So you want to keep your echo train length kind of tight. When I go T2, now I can use the longer echo train length and I can take all those averages of my TE because they're longer. I've got a better range. Okay, so fast spin echo, T1, short echo train length, proton density, a medium, in the middle, and then T2, we can use the longer echo train lengths. Now, another important fact to know about echo train length is as you increase your echo train length, you also increase the chance of blurriness on the image. Because you have these longer ranges of TEs, you're also going to increase some blurriness on the image, okay? You may not be able to see it, but a radiologist will see it. Okay, so we kind of stay 15 to 25, 27. Again, as you go higher than that, yeah, your scan time is going to go down, but you're also going to increase blurriness because of all those multiple TEs that get averaged. So getting back to this, if you see this diagram, 90, 180, 180. It doesn't matter if there's 2 here or 4 there. As long as you see more than 180, this means fast spin echo. Here we go with the echo train lengths again. So let's say we have an echo train length of 8. There will be 8 180 rephasing pulses per TR. 8 lines of case space get filled per TR. That's what makes it quicker, okay? Because we know that the image is complete once all the lines of case space get filled. So scan time is going to be 1/8 on a fast spin echo. It's going to be 1/8 of the time that was performed on a spin echo. So to figure out your timing, you're going to take your TR times your phase encodings times your next. That's our scan time for a conventional spin echo. TR times phase encodings times next. If you do a fast spin echo, now you're going to divide the next by the echo train length. Okay? So you're going to take TR times phase encoding times next, and you're going to divide it all by the echo train length. And you're going to get, depending on the echo train length, it'll be 1/8. If it's 8 echo train length, it'll be 1/8 the time of a conventional spin echo. Let's say you have echo train length of 10. It'll be 1/10 the time from a conventional spin echo. Does that make sense? So you take your TR times your phase encodings times your next, and you divide it by whatever your echo train length number is. Echo train length is also known as turbo factor on Siemens, Philips. Okay, again, I don't know exactly which chapter it is in the book, but there is a chart in there that will